Okay, so here I'm going to look at sort of one big combined problem focusing on solubility and solubility product constants and precipitation, specifically selective precipitation, right? Which lets us separate ions that are already in a solution in a way using, right, solubility and solubility product constants. Okay, so let's consider this problem, right? We have a solution, right? Maybe it's some industrial waste, right? Something that contains lead ions, copper ions, and silver ions, right? At these concentrations. But some of these are valuable. Actually, all of them could be valuable, and we'd like to recover them and separate them. So our question is, how can we selectively precipitate these ions to achieve as much separation as possible? And so we think, right, one of the ways we can precipitate them. So we need to think about some ion that would precipitate one or all of them. And I came up with the bromide ion, that we could use sodium bromide to add bromide ion, because each of those ions makes a bromide ion compound that we consider to be insoluble, right? They have small values of the KSP, and so we consider each one of these, if we go back to our solubility rules, right, would be an exception to the halide salts are soluble rule. Remember, it's most halide salts are soluble except copper 1 was an exception, silver was an exception, lead 2 was an exception, right? So we know those are insoluble. We can look up the KSP, right? So that's the setup to our problem, right? You'll need to write down those facts, and we'll go through and we will work through this problem to see how well we can separate these using selective precipitation with sodium bromide. The first thing we do is find the threshold concentration of bromide ion that for each cation to precipitate, right? That is, when will Q for each metal bromide equal the KSP for that metal bromide, right? So let's consider, right, our copper bromide, right? So our concentration of copper ion, we said, was 0.40 molar. Our KSP for copper bromide was 6.27 times 10 to the minus 9. And so, right, copper bromide dissociates 1 to 1. That's solid to make copper ion. Plus bromide ion. So our KSP would be equal to the concentration of copper ion times the concentration of bromide ion, right? And that is equal to that 6.27 times 10 to the minus 9. And we know the concentration of copper ion is 0.40. So we've got 0.40 molar times the concentration of bromide ion equals 6.27 times 10 to the minus 9. Concentration of bromide ion will equal 6.27 times 10 to the minus 9 divided by our 0.40, and that will equal 1.5675 times 10 to the minus 8th molar, right? So when our bromide ion gets up to this concentration, copper ions will begin to precipitate, right? This is our threshold, right? If these go above this, then Q will be greater than our solubility product constant, and precipitation will begin. So now we'll do the same thing for the other two ions. Okay, so if we're focusing on our lead ion, we said our lead ion concentration is 0.20 molar. We know the KSP of our lead 2 bromide is 4.67 times 10 to the minus 6. Right? If we write out our dissociation of our lead bromide, right, that's solid, is going to form lead 2 ions and 2 bromide ions. Right? So the form of our KSP is going to be equal to the concentration of lead ions in our solution times the concentration of bromide ions squared, right? Remembering our coefficient. Right? We know our concentration of lead ions, so our 4.67 times 10 to the minus 6 is going to be equal to our concentration of lead ions, 0.20, times the concentration of bromide ions squared. So 4.67 times 10 to the minus 6 divided by 0.20 is equal to the concentration of our bromide ions squared, which equals 2.335 times 10 to the minus 5. But remember, that's bromide ion squared. So the concentration of bromide ion is going to equal the square root of that 2.335 times 10 to the minus 5, which is equal to 4.83, let's go 2 times 10 to the minus 3 molar, right? So when our bromide ion concentration gets up to 4.832 times 10 to the minus 3 molar, lead ions will begin to precipitate. That is our threshold concentration, right? At that concentration, right, our Q is equal to our KSP. If we exceed that concentration, Q will be greater than KSP, and we will begin to precipitate. Right? So now we have to consider our silver ions. Okay, now if we consider our silver ions, right? We said our concentration of silver ions is low, 6 times 10 to the minus 6 molar, right? And we know we were given the KSP for silver bromide, but we could have looked that up at 5.35 times 10 to the minus 13. Right? So if we look at our dissociation for silver bromide, solid, will dissociate to form silver ions plus bromide ions, right? And our KSP is going to be concentration of silver ions times the concentration of bromide ions, each raised to the first power, right? And we know that our KSP is 5.35 times 10 to the minus 13, and that's going to be equal to, we know our concentration of silver ions, 6.0 times 10 to the minus 6 times the concentration of bromide ions, right? So 5.35 times 10 to the minus 13 divided by 6.0 times 10 to the minus 6 equals the concentration of bromide ions, which is equal to about 8.917 times 10 to the minus 8. And that's molar. So when we get to 8.917 times 10 to the minus 8th molar, our silver ions will begin to precipitate. If we gather our results together, right, we can see, right, we found that copper ions will begin to precipitate when the bromide ion concentration reaches about 1.57 times 10 to the minus 8th molar. Lead ions will begin to precipitate when the bromide ion concentration reaches about 4.8 times 10 to the minus 3 molar, much higher than that. And silver ions will begin to precipitate when bromide ion reaches about 8.9 times 10 to the minus 8th molar, right, which is a little bit higher than that, right? So if we look at this, right, copper ions will precipitate first at the lowest concentration of bromide ions. Silver ions will precipitate second, and then lead ions will precipitate third. Okay? So, now we're going to ask another question, right? So, when the concentration of bromide ion gets to number 2, that is, begin to precipitate silver ions, how much copper ion will be left? Okay? All right, well, our KSP for copper bromide is 6.27 times 10 to the minus 9 molar, and our concentration of bromide ion will be this. So our concentration of copper ion will be 6.27 times 10 to the minus 9 divided by that concentration of copper ion, 8.917 times 10 to the minus 8th, and we get 0.070315 molar, right? So when silver ion starts to precipitate, there will still be 0.07 molar copper ion in solution, right? And so if we take our, right, we had 0.40 molar at the beginning. We now have 0.070 approximately left, which means we recovered 0.33 molar was recovered as precipitated copper bromide, right? So we recovered, right, as I'm running out of space here, right, 0.33 over 0.44 times 100% is 82.5% of our copper was recovered as copper 1 bromide precipitated. Okay? So now we'll look at the other two, right? All right, so now we consider the next transition, right? So when our bromide ion gets up to concentration 3, that is, when it begins to precipitate lead ions, at that concentration, how much copper ion and how much silver ion will be left in solution, right? Well, we know that when we get to 3, the concentration of bromide ion is 4.8 4.832 times 10 to the minus 3 molar, right? That's what we had determined earlier, right? So if we look at our KSP for copper bromide, right, it's going to be 6.27 times 10 to the minus 9 is going to be equal to the copper ion concentration that we don't know, times the bromide ion concentration that we said was 4.832 times 10 to the minus 3. Right? So the concentration of copper ion will be 6.27 times 10 to the minus 9 divided by 4.832 times 10 to the minus 3, and we get 1.2976 times 10 to the minus 6 molar. Okay? And if we do the same thing then with silver ion, right? Our KSP for silver bromide is equal to 5.35 times 10 to the minus 13, right? That's going to be equal to the concentration of silver ion times the concentration of bromide ion, which at that point is 4.832 times 10 to the minus 3. So our concentration of silver ion is 5.35 times 10 to the minus 13 divided by 4.832 times 10 to the minus 7, which gives us 1.1072 times 10 to the minus 10 molar silver ions. Okay, so let's look and bring together our results again and look at them. Right? When we reach point 2, that is when silver ions are going to begin to precipitate, our concentration of bromide ion was 8.917 times 10 to the minus 8th, and yes, I know we're carrying extra significant figures. Our concentration of copper ion is just a little more than 7 times 10 to the minus 2 molar, right? And our concentration of silver ion is still 6 times 10 to the minus 6 because it hasn't started to precipitate yet. When we exceed this concentration, then silver ions will begin to precipitate. But copper ions will continue to precipitate as the bromide ion concentration goes up. Now, when we reach point 3, just at that moment before lead ions begin to precipitate, our bromide ion concentration has gone up from 8.917 times 10 to the minus 8th to 4.8 times 10 to the minus 3. Right? It's gone up a lot. Our copper ion concentration has fallen from 7 times 10 to the minus 2 down to 1.3 times 10 to the minus 6. And our silver ion concentration has gone from 6 times 10 to the minus 6 down to 1.1 times 10 to the minus 10, right? It's gone down a lot. So if we look at how much these went down, right, our copper ion concentration went down by about 7.03137 times 10 to the minus 2, right? And our silver ion concentration went down by about 5.99989 times 10 to the minus 6, right? Which means, right, this many moles per liter precipitated, right? This many moles per liter of our solution precipitated. So our first question is, right, we've collected some copper bromide precipitate and some silver bromide precipitate, right? Represented by these two numbers, right? So our total precipitate is going to be the sum of those two, right? So our total precipitate is 7.03197 times 10 to the minus 2 moles. Right? So if we take that, if we divide our amount of silver bromide precipitate in moles by our total, we're going to get 5.99989 times 10 to the minus 6th divided by 7.03197 times 10 to the minus 2. That's going to be a little number. 8.53 times 10 to the minus 5, or 0.00853%, right? And that was copper bromide to the total. So the precipitate we recovered in the middle is less than 1/1000th of 1% silver ion. So we were not able to separate our silver ion from our copper ion. We precipitated most of our silver ion, but in that range where we were precipitating silver ion, we were also precipitating copper ion, and so we failed to separate copper ion from silver ion, right? That's important to be able to figure out. Okay, so now we've precipitated most of our copper ion, most of our silver ion. So say we want to recover 99.9% of our lead ion, right? So to what concentration would we need to raise the concentration of bromide ion to do that? Well, if 99.9% precipitates, then we want to have 0.1%, right, which is 0.1 over 100, right, percent is going to be left from our 0.20 molar that we had at the beginning, which means there would be 2.0 times 10 to the minus 4 molar lead ion left in solution, right? When we reach that 99.9% recovery rate, right? Okay, so if we use the KSP of our lead 2 bromide is going to be equal to the concentration of lead times the concentration of bromide ion squared, right? Remember the stoichiometry, right, of that dissociation. And we said that was equal to 4.67 times 10 to the minus 6. So our 4.67 times 10 to the minus 6 is going to be equal to 2.0 times 10 to the minus 4 times the concentration of bromide ion squared. So 4.67 times 10 to the minus 6 divided by 2.0 times 10 to the minus 4 is going to equal 2.335 times 10 to the minus 2, but that's equal to the concentration of bromide ion squared, so the concentration of bromide ion will equal 1.528 times 10 to the minus 1 molar. Okay? So there's another thing we can do with this problem, right? We can just keep building on this same problem. I got one more thing I want to do. Okay, so, in that last problem, we talked about recovering 99.9% of our lead. And when we said when we covered 99.9% of our lead, the concentration of lead left would be 2.0 times 10 to the minus 4 molar, right? But we said the concentration of bromide ion would be 1.528 times 10 to the minus 1 molar. So if there's that much bromide ion, can we figure out how much copper ion is left and how much silver ion would be left? Well, sure we can, right? Because we know the KSP for our copper bromide is 6.27 times 10 to the minus 9. So we've done this a couple of times. So our concentration of copper ion will be equal to our KSP divided by the concentration of bromide ion. So it's going to be 6.27 times 10 to the minus 9 divided by that 1.528 times 10 to the minus 1, which equals just about 4.1 times 10 to the minus 8th molar copper ion left. If we do the same thing then with silver ion, right, our KSP for our silver bromide was 5.35 times 10 to the minus 13, right? So our concentration of silver ion is going to be equal to that KSP, 5.35 times 10 to the minus 13, divided by the concentration of our bromide ion, which is 1.528 times 10 to the minus 1, and we get that there's about 3.5 times 10 to the minus 12 molar, silver ion left, right? This was copper ion left. So I hope this showed you some variations of things we can do with selective precipitation, right? There's, finding the threshold, right? That's important. There's finding the amount of one thing that is recovered when we reach the threshold for the next component, right? And then there's the question of purity when we've got multiple things precipitating. So there's a lot in this. You really should go through and work through each of these parts as I'm working it to make sure you understand how to do this.